Good evening, sir. So, good evening, Kiran, sir.
Sir, good evening, sir.
Good evening, sir. Okay, sir. Start, sir, section.
Shall we start?
Yes, sir. Start, sir.
Yeah, or we'll wait for some more time.
No problem, sir. You
What
start,
is
sir. I think.
there?
Okay, sir.
Okay.
Okay. Thanks.
Let us start the session. Good evening, all. Welcome to the third day. Today we are going to practice MATLAB implementation of power electronic converters using MATLAB Simulink. Implementation of power electronic converters using MATLAB Simulink. So we'll simulate from the basic converter. First I'll explain how to simulate a conventional three phase 2-level inverter, and then we will see 3-level inverter, and then we will see 5-level inverter. Okay. So before uh, going in detail, I'll just explain the procedure to develop the model, and then we'll go to the simulation. 1 minute, please. Yes, let me share my screen first. Yes, is my screen visible?
Yes, sir. Visible, sir. Yes, sir. Visible, sir.
Okay, thank you. Uh, yes. So a conventional three-phase two-level inverter. We have seen about this three-phase two-level inverter. The circuit diagram. This is the circuit diagram. So here once again I'll take. Yes. So here this is the circuit diagram. A conventional three-phase two-level inverter. Okay, that means here if you see S11 and S12 are forming one phase. Okay, S11 and S12 are forming one phase. S13 and S14 are forming another phase. 15 and 16 are forming a C phase. Okay, now so this is A phase, this is B phase, and C phase. How do we generate the gating signal to all these phases? For the first phase, we will see for the first phase, and I will tell you how to generate the gating pulses to the B phase and C phase. Okay, even though you know about the generation of gating pulses to this inverter, let me by keeping in mind all the participants, I'll explain the basic converter, and then based on these steps, what I am going to explain here step by step, the same steps are applicable to the remaining converters also. That is why I'll take time to explain everything here. So for A phase, uh, in order to generate the gating signal for A phase, I need one modulating signal and one carrier signal. Modulating signal is a sine wave, carrier signal is a triangular wave. Triangular wave. Okay, so we are going to generate the carrier wave and modulating wave. These are very simple, sine wave and triangular wave we can generate easily, and we can give it to the A phase. How do we generate this gating signal from using modulating signal and carrier signal is, if the modulating signal is greater than or equal to carrier signal, the output should be high. We write this logic, and this logic is given to S1. Okay, and if the modulating signal is less than carrier signal, that will be given to switch S2. Okay, switch S2. The same thing you for switch S2 can be generated from this signal also. If you take this signal and give it to the NOT gate, that will also generate the same signal here for S2. Okay, so this is how we generate the gating signal for S11 and S12 A phase switches. For B phase switches, just we take the carrier signal as it is, and we change the modulating signal phase delay by 120 degrees. That means I'll take different color. That means we'll start the waveform here. This is B phase waveform. We'll start the B phase 120 degrees because the phase displacement between A phase and B phase is 120. Similarly, for C phase, we'll take another 120. That means 120 plus 120, 240 degrees. 240 degrees, but the triangular wave is same. Okay, this is what we are going to design. We are going to implement with MATLAB Simulink. Okay, now see, you know switches IGBTs here, S1, S2, S3, S4, S5, S6, and all these are connected to the DC source, and each phase is connected to an RL load. Okay, here three RL loads are connected in a star connection, and now see here, till this part till this part it is a power circuit. You can see now the parameters in the power elements in the power circuit. DC source is a power circuit element, switches IGBTs power circuit elements, and all these loads are power circuit elements. Now we will see measuring devices. What are the measuring devices? Voltages and currents. Okay, now what voltage I am going to measure? Phase voltage. First phase voltage, A phase to neutral voltage. Second one, line to line voltage. That means A phase to B phase voltage. Okay, this is given to second channel in a scope. Third one also I am going to measure, that is current in a phase. Current in A phase. Okay, and I give this current to the scope. I'll take one more channel in the scope. Three. Now I'll give this current to the third channel. Right? Till now we have seen power circuit elements and measuring elements. Now we are going to see control circuit elements or signal elements. Okay, so signal elements, what I told you here, we need three sine waves, one sine wave and one triangular wave for each phase. So now here I am taking one sine wave which is having a magnitude of 1 and frequency 2 pi into f, that means 50 hertz frequency. Phase delay is 0 for A phase. Okay, the triangular wave is -1 to 1. It is varying from -1 to 1, and 1 0.5 into e minus 3 and 1 e minus 3, representing 1 kilohertz switching frequency, which I have explained in the day 1 how to generate the gating signal. With this, what I told you, the logic, if the sine wave is greater than the triangular wave, the first terminal is connected to sine wave, second terminal is connected to triangular wave. So this block generates, if the sine wave is greater than the triangular wave, it generates high. So we are giving the same signal to S1. Okay, if it is less than, then that is given to S2. Okay, now similarly the same thing is copied and pasted again, and only change in the parameters are amplitude is 1 only, frequency is 2 pi into f only, but the phase delay is 2 pi by 3, that is equal to 120 degrees. Remaining everything is same. Okay, here also everything is same. Similarly, these are given to S3 and S4, that means B phase switches. Similarly here C phase, everything is same, magnitude is same, frequency is same, the phase delay is 4 pi by 3, that is 240 degrees. 240 degrees. And now these are the elements. These are the go to element and from element, go to block and from block. This go to block receives the signal from this block greater than or equal to block and pass this signal wherever you use the same S1 from the block. Okay, that means here you have to give S1. If you give S1 here, then it will take the signal from go to block of particular S1. Okay, so similarly here you have S2, that signal is taken from here. Okay, similarly for B phase we are giving from go to block of S3 and S4. Okay, one more thing you have to remember here is, when you click on this block, here you have to select global. If you use a subsystem, if you use from one system to another system, the same signal from one system to another system, then you have to use here global, otherwise you have to click local. Okay, now we are passing this signal to the other system, that means this is separate block, this is a separate space, so we are taking here it as a global. Okay, otherwise if you have a sine wave and triangular wave here in the same space, same page, then you have to select local. Now then everything is over, you have to simulate this one. and select, instead of 10 seconds you can select 0.1 second also. Zero point 0.1 second means okay, otherwise we will take 0.5 seconds. We'll simulate. Remember here, first one is phase voltage, second one is line voltage, third one is phase current. Okay, these are the three waveforms we are going to see here. Yeah, something, we'll check it out once. Ten 50, 1050 and 1050 E minus 3. Phase voltage, line voltage and phase currents. Now before that in this pulse generators, S1, S2, S3, S4, S5 and S6. Now S1, S2, S3, S4, S5, S6 all are global. This is global. Right. We'll go to configuration parameters and we'll see the parameters how it is designed. Yes, here 1 E minus 6. Maximum step size should be 1 E minus 6. Now, in order to validate our sine waves, whether all these sine waves are correctly taken or not, give all sine waves to 3 different ports and take one triangular wave also. Here you can clearly see yeah, it is taking more time, so we will take 0.1. Yes, now click on this. You will see 3 sine waves, 3 phase sine waves. That means all sine waves are correctly taken. Modulating signals, all 3 phase modulating signals are correctly taken, and triangular wave is also designed for 1 kilohertz. So there is no problem in selecting the gating signal. Now look at the scope. Yeah, this is what the 3 phase signals are. This is all about a 3 phase. This is a 3 phase voltage, this is a line voltage, and this is the phase current. This is how you have to simulate a 3 phase 2 level inverter, conventional 2 level inverter. Okay, this is the basic block, and you may be knowing about it, but the next step what we are going to do is simulation of single phase 3 level inverter. Simulation of single phase 3-level inverter. Okay. Now, before that, we can even simulate single phase 2-level inverter also, half bridge inverter. Okay, I'll take now. Otherwise, we can simulate here itself. We can simulate here itself. I'll take one more file, save it as desktop, half bridge. So here, half bridge inverter. How do we model half bridge inverter? Just we will take delete and let us consider only one resistor, one load, and the half bridge inverter configuration looks like this. It consists of two DC sources. It consists of two DC sources connected like this, and in between load is connected. Okay, hence you have to take current measuring device also. Here take current measuring device, connect here, and voltage measuring device, connect here. Voltage is between positive and negative terminals of the load. So now you can take another scope, paste here. It requires two signals. One is for voltage measurement, second one is for current measurement. This is for voltage measurement and this is for current measurement. Now here we need only one phase, A phase only. Okay, so however B phase and C phase we are not using. So just if you simulate, you will get the voltage and current waveform. This is the two-level inverter voltage waveform. This is the two-level inverter voltage waveform. Okay, so how the voltage waveform is varying? Yeah, I'll take auto scale. Yes, this is the voltage waveform and this is the current waveform. If you see here, the voltage is varying from minus 100 to plus 100. The voltage is varying from minus 100 to plus 100. So dV is high, dV by dt is high, and so you can see the current ripple how it is, how the ripple content is more in two level inverter. The same thing we will simulate for full bridge inverter and then we will see the results. Okay, I will take it as I'll save it as full bridge. Full bridge, and then what are the differences you find here from half bridge to full bridge? That is the variation in the load connections as well as the number of switching devices also. Here you are using only S1 and S2. In the full bridge, you need 4 switching devices. In the full bridge, you need 4 switching devices. So, I am taking 2 switching devices and I will connect here. Here. So now, this is the load. Load will be connected in between the 2 switching devices. This is the load connection. Now, the next point is voltage terminal connection. So now, I will give the voltage to the first terminal and current to the second terminal. Okay, this is the power connection, power signal connection. Here I will take S1 and S2. Here the second leg of the inverter is taken as S3 and S4. S4, right? Now I'll simulate this. Here in the full bridge, you don't require 2 DC sources, 1 DC source is sufficient. Now I move this to left side. Yeah, coming to pulse width modulation technique. In the pulse width modulation techniques, we are using S1, S2, S3, S4, 4 switching devices. So here the logic is, this is also called as full bridge inverter as well as a 3-level inverter. This is also called as a 3-level inverter. This is a 3-level inverter. Okay, how do we generate gating signal for 3-level inverter? That we will see now. In order to generate gating signal for 3-level inverter, the minimum requirement is one modulating signal, and 2 carrier signals. Carrier signal is nothing but a triangular wave. That means triangular wave is varying from 0 to 1, 0 to 1. The second triangular wave is varying from -1 to 0. The second triangular wave is varying from -1 to 0. That means you need one modulating signal and two carrier signals, two triangular waves. How do we generate these modulating signals that we will see in this pulse width modulation technique? And then before going into the logic, how do we generate the gating signal, that we will see now. Okay, I'll take it as a carrier signal C1, and I'll take this carrier signal as C2, and this modulating signal as M. Okay, suppose if M is greater than or equal to C1, I will generate one gating pulse that is equal to VDC plus VDC plus VDC. Suppose if the modulating signal is less than first carrier wave and it is greater than the second carrier wave, then I'll generate the modulating signal that is equal to C1 is greater than modulating signal, and modulating signal is greater than C2. That means M is less than C1 and greater than C2. Then the generated pulse is equal to 0 voltage level. Similarly, if C2 is greater than M or M is less than C2, that pulse, gating pulse, is related to minus VDC. Minus VDC. So, from gating pulse point of view, we have seen the logic how to generate the gating pulses for VDC level and 0 voltage level and minus VDC voltage level. But now we have to analyze the circuit and we have to see what are the switching devices which are conducting during these voltage levels. Okay, so now this is the circuit, this is the full bridge inverter, this is S1, this is S2, and this is S3, and this is S4. Here we have a load terminal S1, S2, S3, S4. Okay, this is VDC. Now, if you turn on S1 and S4, then yesterday we have seen the analysis of this converter. If you turn on S1 and S4, then you are getting plus VDC. Okay, so for plus VDC, you have to turn on, write down the switches here, S1, S2, S3, S4. Okay, S4. Now, for plus VDC, which are the devices that are in conduction? S1 and S4. So, keep 1, 1. Okay. Now, for 0 voltage levels, which are the devices that are conducting? We have to see. We can turn on S1 and S3. S1 and S3, then it will be connected here. This terminal will be connected here, short circuit, so 0 voltage. Or you can take S2 and S4. S2 and S4. Okay. So if you turn on S2, it will be connected here, and S4 it will be connected here. So S2 and S4. Okay. Similarly, for minus VDC, so first terminal must be connected to the bottom, so you have to turn on S2, and the second terminal must be connected to top side, so you have to turn on S3 and S2, S3 and S2. Okay, so after preparing this table and this table, you can correlate the switching pulses. So see here, see this table. S1 is only turned on during the positive VDC, plus VDC only. S1 is turned on during plus VDC only. Okay, so what I will do is, whatever the pulse that I am getting here, this is directly given to S1. This is directly given to S1. Now see here S2. In case of S2, S2 is switched during 0 voltage level and during minus VDC voltage level also. Okay, in both the cases S2 is turned on. So what I will do is, I will take both the signals and I will give it to the OR gate, and this is given to S2. Okay, similarly for the switch S3, S3 is turned on only during minus VDC. Okay, so I'll give the same signal to S3 directly. Okay, and coming to S4, S4 is turned on for plus VDC by 2 and 0 voltage level. So plus VDC by 2 signal and 0 voltage signal both are given to OR gate, and resultant gating signal are given to S4. Okay, this is how you have to generate the gating signal, and you have to give it to the switch corresponding switches. Is it clear? If it is clear, then only we can go to the implementation part. Otherwise, if you have any doubt, please let me know. I'll repeat once again. If you don't have, if it is clear, then we'll go to the implementation part. This is the full bridge inverter or a 3-level inverter where 4 switches are connected together. So here we will generate one sine wave and two carrier waves. Sine wave is designed for 1 to minus 1. Carrier wave, this is designed for minus 1 to plus 1. But now in 3-phase, we are generating only for 0 to 1. This is designed for minus 1 to 0. Minus 1, 0, minus 1. Now, what is the logic that we are discussing here? If a modulating signal is greater than C1, then it is VDC. If the modulating signal is greater than, this is C1. I'll write here as C1. This is C2. Okay. Now, if it is greater than the first carrier wave, then this is equivalent to plus VDC. Okay. Now, what is the second logic? How to generate signal related to 0 voltage level? That means modulating signal should be less than the first carrier wave and greater than or equal to second carrier wave. Both should be happened. Okay, so this is less than first carrier wave, and it should also be greater than or equal to second carrier wave. Both should happen. Okay, this is not OR operation. Both should happen. Hence it is AND operation. Okay, that means we have to go to Simulink library and find gating gates block. That block you can find here, uh, logic bit operations. So here in the logic bit operations, see here you have a relational operator and logical operator. Take it. So as AND operation is required, so keep it as a AND operator. So this is related to zero voltage level. Okay. Now the last one is the voltage level corresponding to minus VDC is M should be less than C2. M should be less than C2. M should be, M means a sine wave, should be less than the second carrier wave C2. Then this is equivalent to the gating signal for minus VDC. Okay, so first part is over. In this generation, logic generation for voltage levels is over. Logic generation for voltage levels is over. Now we have to generate these logics here. Okay, what is given to S1? Directly VDC is given to S1. So VDC, this VDC directly we give it to S1. So I will connect here directly S1. Okay, next, what is given to S2? What is given to S2? VDC and also zero voltage level. Okay, in both the cases it has to operate. This is S4. S2 should be operated between zero voltage level and minus VDC voltage level. So I'll take here same gate 0 and 0 and minus VDC is given to S2. Okay, now we will see what is S3. S3 minus VDC is directly given to S3. See, this is minus VDC, so it can be directly given to S3. Done. Coming to S4. What is given to S4? Plus VDC and also zero voltage level. Both are given to S4. Okay, this is OR gate. In both the cases it should be operated. So we will take it as OR gate. Next, for S4 we are giving plus VDC and 0. S4. Okay, so this is how we have to generate the gating signals, and in order to see whether whatever we have given is correct or not, so we'll take one sine wave and two carrier waves. So three signals are required. So this is given to sine wave. This is taken from the carrier wave. This is taken from the second carrier wave C2, and then we will simulate. Run the simulation and see whether your given sine wave and carrier waves are in the sequence or not. Yeah, this is what we have given. So I'll zoom it. One sine wave and two carrier waves. First carrier wave is varying from 0 to 1, and the second carrier wave is varying from -1 to 0, and sine wave is varying from 1 to -1. Yeah, correct gating, correct modulating signal and carrier waves are selected. Now see the voltage and currents. Yeah, this is the voltage waveform. See, the voltage is varying from 0 to 100. The voltage is varying from 0 to 100. Here 0 to -100. dV is only 100. In case of previous circuit, it is varying directly from -100 to +100. So dV is 200. Here dV variation in the voltage is only 100. Okay. And one more thing, if you observe here, from 2 level to 3 level, the peak spikes, the ripple content, the variation in the current is somewhat less compared to the single phase 2 level inverter. In the single phase 2 level inverter, this ripple content is significantly high, whereas in the 3 level inverter it is less. Okay. Similarly, if you see the 5 level inverter, ripple content in the inverter current is significantly less. Ripple content in the inverter current is significantly less in the 5 level inverter. That we will see now. Yeah, this is a 5 level inverter wherein 4 switching devices, 4 conventional switching devices and 1 bidirectional switch is taken, and the logic to generate 5 voltage levels is the logic to generate 5 voltage levels. I will explain here. I will draw the circuit. I will take 2 DC sources and a full bridge inverter. Here in between we are connecting a bidirectional switch. Okay, this is S1, S2, S3, S4 and this is S5. In between we are connecting a load. Okay, so this is VDC and this is another VDC. How we are generating 5 voltage levels, that we will see now. Okay, so in order to generate 2 VDC, what are the 5 voltage levels? 2 VDC, VDC, 0, minus VDC, and minus 2 VDC. These are the different voltage levels. In order to generate 2 VDC, what are the switches that are conducting? I'll write here S1, S2, S3, S4, S5. Okay, so 2 VDC, in order to generate 2 VDC, your first terminal 1, this is 1 dash. 1, in order to connect 1 here, you have to turn on S1. Okay, and in order to connect 1 dash here, you have to turn on S4. Okay, then the equivalent circuit looks like this, and the load is connected between two voltage sources. So voltage appeared across V0, load voltage, is equal to VDC plus VDC to VDC. Okay, in order to generate gating pulses, in order to generate 2 VDC across the load, you have to turn on only two switches, S1 and S4. S1 and S4. Okay, we can make a tabular column also. Yes. Now you are conducting only S1 and S4 for 2 VDC. So for plus VDC, you can turn on S5. You can turn on S5. Then terminal 1 is connected here. You can turn on S4. Then 1 dash will be connected here. Okay, I am drawing only, otherwise I will draw two VDCs, DC sources, and the load is connected like this. Okay, so here S5 is turned on, here S4 is turned on. Okay, so S4 and S5. So to generate 0 voltage level, if you turn on S4, S2 and S4, then the two terminals are short circuited, then 0 voltage will be applied across the load. So in order to generate 0 voltage, we have to turn on S2 and S4. S2 and S4. Next voltage level is minus VDC. In order to generate minus VDC voltage level, see the possibilities. You can turn on S5, you can turn on S5, and you can turn on S3. If you turn on S3, 1 dash will be connected here. 1 dash will be connected here, and 1 will be connected here. Okay, in this way you can generate minus VDC. That means this is the equivalent circuit, 1 and 1 dash. So here for minus VDC, what are the devices that are conducting? S5 and S3. S3 and S5. Similarly, for minus 2 VDC, you have to turn on S2 and S3. S2 and S3. Then the equivalent circuit looks like this. This is VDC and this is VDC. 1 dash is connected to top and 1 is connected to bottom. So minus 2 VDC is applied. So for minus 2 VDC, we are turning on S2 and S3. This is S2 and this is S3. Okay. So first, for simulating any multi-level inverter, first you have to prepare this table. First you have to prepare this table, and then based on this table you have to generate the gating signal from sine wave and triangular wave, and then you have to give it to the OR gate to generate the total signal. That means S1 is conducting only during 2 VDC by 2 VDC level. So whatever the 2 VDC voltage signal you are getting, you can directly give it to S1. So here in case of S2, it is conducting during 0 voltage level and 2 VDC minus 2 VDC voltage level. So you have to add these two signals, 0 voltage signal and minus 2 voltage signal, both together should be given to S2, switch S2. Similarly for S3, minus VDC level and minus 2 VDC level signals are given to S3. For S4, 2 VDC, VDC and 0 voltage levels are given to S4. For S5, VDC and minus VDC voltage levels with signals are given to S5. Okay, so now we will see how to generate gating signal for 5 level inverter, 2 VDC gating signal and VDC gating signal and so on. Okay, so for 5 level inverter, you need one modulating signal and 4 carrier signals. How to find out the number of carrier signals required? That is equal to number of levels minus 1. Number of levels minus 1. So it is 5 level inverter. So you need 4 carrier signals. For 7 level inverter, you need 6 carrier signals. Okay. So as it is a 5 level inverter, we divide the regions into 4 different regions. So this is sine wave is varying from 1 to minus 1 only. The first carrier wave is varying from 0 to 0.5, 0, 0.5, and second carrier wave is varying from 0.5 to 1. 0.5 to 1. Similarly, the next carrier wave is varying from minus 0.5 to 0. The last carrier wave is varying from minus 1 to minus 0.5. So I'll take this as C1, I'll take this as C2, and this is C3, this is C4. Okay, this is modulating signal M. The logic is same. If M is greater than or equal to C1, this is equal to 2 VDC. If C1 is less than M and M is less than C1 and greater than C2, this is VDC. C2 is greater than M is greater than or equal to C3, 0 voltage level. C3 greater than M greater than or equal to C4, that is minus VDC. If C4 is greater than M, then that is equal to minus 2 VDC. So first we have to generate all these voltage levels from the modulating signal and carrier signal, and then we have to add or merge the gating pulses to generate appropriate gating signal. First we will see how do we generate these logics using the MATLAB Simulink. Before that, we will generate this sine wave and 4 triangular waves first. This is step 1 and this is step 2, and step 3 is addition of different gating signals. This is step 3. This is step 3. Okay, adding the different voltage levels to give it to the particular switch. Okay, now we will see here. These are the different triangular waves. Okay, so here I have taken 2 to minus 2 sine wave. I have taken from 2 to minus 2. So the triangular wave and sine wave, you can take it here. Yes. So sine wave is varying from, this is 0, you can take, this is 1, this is 2, this is minus 1, minus 2. Okay, so anything is okay. You can vary the sine wave from 0 to 1 or 0 to 2. If you vary that sine wave, you have to vary the magnitudes of triangular waves also proportionally. Okay, now here the circuit is designed S1, S2 and S3 and S4, 4 switching devices, and this is S5. Okay, all together is S5. Okay, 2 DC sources are taken. Now we will see how we are generating the gating signal. Yeah. So 4 triangular waves are taken, and if a sine wave is greater than the first triangular wave, this is equal to 2 VDC, and if the sine wave is less than the first triangular wave and greater than the second triangular wave, both are given to AND gate. In this case, we take it as V plus VDC, and if it is greater than, sine wave is less than the second carrier wave and greater than the third carrier wave, this is taken as 0 voltage level, and if it is less than the third carrier wave and greater than the fourth carrier wave, that is taken it as minus VDC, and if it is less than the last carrier wave, then it is taken it as minus 2 VDC. Okay, this is the logic we follow. Then after generating the voltage levels, follow this. So S1, only 2 VDC voltage level is given to S1. See here, no, this is not the case. Yeah, see here, only 2 VDC signal is given to S1. Coming to S2, 0 voltage level and 2 VDC voltage level. 0 voltage level, see this is 0 voltage level given to first terminal. second terminal is given to minus 2 VDC level, right? Both are given to OR gate and given to the respective switch S2. Coming to S3, S3 minus VDC and minus 2 VDC. S3, where is S3? This is S3. See, minus VDC is given, minus 2 VDC is given. Okay, so this is given to S3. Coming to S4, S4 2 VDC, VDC 0. S4, see, this is 2 VDC, this is VDC, and this is VDC, and this is 0. Okay, all three together given to S4. Coming to S5, this is S5. It is turned on during VDC voltage level and minus VDC voltage level, minus VDC and plus VDC. S5. See, this is plus VDC. You can see this is plus VDC is given and minus VDC is also given, okay, to S5. So after giving the gating signal, then we can run the simulation. Take only up to 0.1 and run the simulation. After completion of the simulation, see, first look at the gating signal, whether you have properly generated or not. Zoom it. Yeah, 1 sine wave and 4 carrier waves. Okay, one is varying from 1 to 2, the second one is varying from 0 to 1, third one is varying from minus 1 to 0, fourth one is varying from minus 2 to minus 1. Okay, so after generating 1 sine wave and 4 carrier waves, then come back to the circuit and see the results. See, you are getting the 5 level voltage waveform. This is 2 VDC, this is VDC, this is 0, this is minus VDC, this is minus 2 VDC. Okay, this is how we generate 5 voltage levels. Now observe the current waveform. Observe the current waveform. Okay, so ripple content in the current waveform is almost 0. Ripple content in the current waveform is almost 0. Whereas in case of 3 level and 2 level, you can find significant component, ripple content component. In case of particularly 2 level, in case of 3 level, it was reduced, and again in case of 5 level, it is significantly reduced. So you are getting pure sine wave in a 5 level inverter. This is the beauty of multi-level inverters. If you go on increasing the number of levels, you will reduce the ripple content furthermore. Okay, this is how we simulate 5 level inverter. Very simple, and if you concentrate some time on this, you can simulate any given converter. Okay, similarly, you can see how a 21 level inverter generates pure sinusoidal voltage waveform. This is a 21 level inverter. So you can take 0.2, that is sufficient, and see the current component. See how sinusoidal it is. Okay, even we will keep 0.5 and we will wait for some time to see the full simulation. Yeah, this is, yeah, now you can see how pure sine wave you are generating with the help of 21 level inverter. Okay, so this is so simple to generate the logic. First you have to follow the step 1 to generate required number of sine waves and required number of carrier waves. For single phase, one modulating signal is sufficient. For three phase, three modulating signals are required. Okay, coming to the carrier waves, either single phase or three phase, number of carrier waves is equal to n minus 1, where n is the number of levels. Okay, so here it is a 21 level inverter and it is generating pure sinusoidal current. Pure sinusoidal current. Even the dV by dt, if you see the dV by dt, it is very, very less. Okay, it is almost 10 volts. 10 volts. Whereas in the same inverter, two level inverter case, it is 200 volts. Here it is, the dV is almost 10 volts. Okay, so this is the beauty of multi-level inverters. So here this is how we can generate the gating signals. If I find time and if I conduct one more session in the coming days, I'll teach you with the help of same multi-level inverters how to generate, how to eliminate the gating signals. That is a very, very interesting topic. So yeah, even we have time, we have 14 minutes more and we can simulate that also very, very easily. It is a simple configuration wherein we can generate, we can eliminate the gating harmonic components. We can eliminate the harmonics without changing any circuit element. Okay, now we will see what are the harmonics present in this circuit. Okay, here SC scope name is given as SC. I'll find out the harmonics present in scope SC. FFT analysis. Go to tools. So how to see the FFT analysis? I'll explain. Listen carefully. Go to continuous block, Power GUI, and go to tools. Click on FFT. A separate page will be opened. Wait a minute, please. Yes. Now you can select scope SC and this is the output voltage, and take starting time period 0.4 and number of cycles you can take one cycle, and frequency is 50 hertz and maximum frequency we will take it as 5000, and we can try for results. Display, click on display. See, all the harmonics are present around 20, right? So I'll take a print screen. Paint. I'll take paint. I'll paste here. Okay. Remember that all the harmonics are concentrated around 20th harmonic in this case. Okay. Now I'll slightly change the PWM concept. Instead of generating gating signal like this. What I'll do is I will take, I'll push everything onto right side. I'll take one sine wave and one triangular wave. This is given to S1 and S2. Similarly, I'll take one more sine wave and triangular wave to this. Okay, and here what I'll do is I'll take the magnitude to 1 and frequency 2 pi f, phase is 0. Here what I'll do is I'll take amplitude 1 only, frequency 2 pi f only, 50 only, but the phase angle displacement I'll take it as pi. Then we will see what is happening to this. When we do like this, what will happen? And we will see what are the modulating signals that we are considering here. So I'll keep here one sine wave and the second sine wave. Both triangulars are same, so I'll take one triangular wave and I'll run the simulation. Yeah, now verify the modulating signals whether you are generating properly or not. Yes, positive sine wave is generated and negative sine wave is generated and only one triangular wave is taken. Then we will see what is happening to the performance of inverter. The same output is generated. Okay, so it is also varying from 100 to 0, 0 to 100 and 0 to minus 100, and the same current is taken, but we will see the analysis here. This is scope SC only. Yes, scope name is SC only. We will see the FFT and we will find out where the harmonics are present. FFT analysis. Yeah, we are starting from 0.4 only and run the simulation. See how beautiful the harmonic spectrum is. From 0 to 40, almost 35, there is no harmonic component. Even a single harmonic component, even of 1% also. But all the harmonics are present around 20. Whereas in the previous case, all the harmonics are present near to 20th harmonic. Okay, so up to 40 there is no harmonic in the other pulse width modulation technique which we are using here. Okay, that means using this pulse width modulation technique, we are cancelling the harmonics without changing any circuit configuration, without changing anything in the circuit. We are eliminating the harmonics. This is the beauty of multi-level inverters and pulse width modulation techniques. You know, in the harmonic cancellation, if you want to eliminate the harmonics, we use a bulk size inductor and bulk size capacitor to filter out the harmonics, but without using any external component. By just changing the logic, we are cancelling the harmonics. That is the beauty of pulse width modulation technique in a multi-level inverters. Okay, so this is what I want to present here. So in future, if we conduct once again, we will discuss some more interesting points related to multi-level inverters. Okay, with this I want to close my I want to stop my presentation. If you have any doubt, you can raise your you can ask me. If you have any doubt, you can ask me. Yeah, one question in the chat box is, what are the applications of multi-level inverters? Multi-level inverters are used wherever we use the conventional inverters. Okay, these are the betterment of better configurations to the conventional inverters. Inverters are mainly used in AC drives, induction motor, speed control, where frequency and voltage are required to be changed proportionally. Okay, so in order to maintain the constant flux, we need to change the frequency and voltage in the same proportion. Okay, in case of AC drives, inverters are used. In the domestic applications, in order to convert the DC power into AC power, we use inverters. Okay, if you have a solar system and solar is generating, PV panels are generating DC power. That DC power is converted back to AC by with the help of inverters. We are using domestic inverters in our house. That inverters convert DC power into AC, and then we are using. Okay, sometimes if you have solar panels, those panels are generating DC power, and it is converted back to AC and given to our home appliances. Sometimes if you don't have solar panels, we used to have domestic inverters with batteries. Okay, battery will store the energy in the form of DC, and again when the power cut happens, then this DC power stored in the battery can be given to our home appliances. That will be converted again to AC and given to uh, given to our home appliances. Okay, like induction heating, and many places we use in even in HVDC applications, where we convert AC to DC at the beginning, and at the consumer end or the load end we convert DC to AC. There inverters are used. Yeah, the second question is, cost is high for multi-level inverters compared to conventional inverters. Very interesting question, and important point also. Very interesting and important also. This is very important. So I'll share my screen once again. Yes. Obviously cost is high, but not so high. I'll tell you the reason. Okay. So here take a conventional two level inverter. Here the load is connected. Here you have a switch. Here you have another switch. This is S1. This is S2. Okay. In place of S1, what we are doing is, in the multi-level inverter configurations, one switch is replaced by many switches. Okay, so it is connected to somewhere to a DC source, multiple DC sources. This is multi-level inverter configuration. Okay, this is all about multi-level inverter configuration. Here somewhere you have a load terminal. Okay, so here if you see what is the voltage rating of this switch? 2V. Voltage rating of the switch is 2V. We have done the detailed analysis in the last class. The rating of the switch is 2V. Okay, the same thing if the input voltage is 100 volts and 100 volts, the voltage here is 2V, and that means 200 volts. Okay, here the same thing, if you take the same comparison, you cannot in order to compare with the same voltage levels, you cannot take that many voltage sources. Here also you can consider 100 volts and 100 volts. Okay, depending on the circuit configuration, these switch in middle connections are connected to the DC sources, but the input voltage level will not be changed. Input voltage level will not be changed. If it is 200 volts input, here also we'll take 200 volts input. Okay, now here instead of one switch, this 200 volts is shared by 3 switches. Okay, otherwise if you take 4 switches, S1, S2, S3, S4, 4 switches are sharing 200 volts. That means each voltage rating of each switch is only 50 volts. Voltage rating of each switch is only 50 volts. That means, in other words, here if you want to place a switch, you need a 200 volts rating switch. Here for the same applications you need 50 volts rating switch. Okay, cost of the 50 volts rating switch is significantly less compared to the cost of 200 volts switch. Okay, for the example only we are discussing this 250 volts. Okay, whereas in case of high HVDC applications we can find 400 volts 400 kV line also. Okay, there you cannot have a single switch in the particular HVDC applications. Okay, that means we have no switch designed till now which can support that much voltage levels. Okay, the maximum voltage rating of the switch is almost around 10 kV. Hence, we cannot it cannot support in the high voltage applications. Uh, so there you have to go to multi-level configuration only, or you have to connect more number of switches in series to withstand the high voltage applications. But your question is, the cost of multi-level inverter is high compared to conventional inverter, obviously. But see, here we need four switching devices. Here you need one switching device. Okay, but cost of one switch is very less compared to 400 volts. As the voltage rating is increasing, the cost of this switch is very high compared to 50 volts switch. Okay, so finally if you calculate, if it is 500 rupees, if it is 500 rupees, it may be around 100 rupees of 200 rupees of each switch. So it is around 1000 rupees. Okay, so it will increase a bit, but not so high, but not so high. As the requirement of voltage requirement is less, the cost of each individual switch is less. Cost of each individual switch is less in case of multi-level inverters. That is the beauty of multi-level inverters. Low voltage rating switches can be used in the high voltage applications. The input voltage is 200 volts, input voltage is 200 volts, but each switch requirement here is only 50 volts. Okay. So similarly, if you increase the more number of levels like 11 level inverter or 13 level inverter, even you can use 10 volts or 15 volts switches also. Yeah. Any other question? I think it is clear. Yeah, if we increase the number of switches, any practical difficulties? Yes, obviously. The practical difficulties are, the first one is reliability, reliability issue, where as you are increasing the number of switching devices, the reliability will be decreased. So you have to take high precautions to for the safety of the switching devices. Okay, you have to take more precautions to take the safety of each switching device. However, snubber is designed for each switch, so there is no issue. Like, the second thing is, we need to generate more number of gating signals. That is also another practical problem. As the number of switching devices increases, you have to generate more number of gating signals. So that is another problem, because the cost of switch is very less compared to the cost of generating the gating signal. Even though these two practical difficulties are there, we go for multi-level inverters because advantages are dominating the disadvantages. Yes, any other question? Thank you, thank you for your comment. Where is it, sir? New Horizon College of Engineering,
Sir, I think they Bangalore.
Bangalore. Good.
Sir, some more questions, sir.
Yeah, I've been receiving calls from some faculty members from yesterday. Yeah, very interesting questions they are asking. Yeah, it is very happy to see you all. Even if you have any doubt, you can contact me or give me a mail. I'll give you a reply. Okay, okay.
Sir, some more question. I think from Vishnu College, sir.
Thank
Vishnu
you.
College. Still, we are using basic inverters. Then, what is the use of going to such high level?
Any other questions?
Sir, some Vishnu College, madam is posted some questions, sir. Vishnu College. Hello.
Sir, Gunashekar sir,
Ah, sir.
if
Yes, sir.
there are no other questions,
Sir,
shall
is there,
we
sir? One
exit?
question. Sir, one question is there. Uh, basic
Yeah,
inverter.
thank you all. Thank you for your active participation.
Thank you, sir.
Yeah, my email ID is kiran triple e 227 at gmail.com. You can contact me at any time.
Kiran, sir.